Section 6.3 is about logarithms, which is one of those topics where once you get the hang of it, you can get it to where it feels pretty natural. But if you've never seen it before, the first time it is kind of weird. So if this is your first time and it looks kind of weird, that's all right. I think that happens to everybody. But basically, what a logarithm is that it's the inverse of an exponential function. And that's what this is supposed to signify here, where if you raise a to the power of y and you get x out, it's the equivalent to saying this, that the way you would read this thing on the right is log to the base a of x, or the log of x with a base a, one of the two, that would be equal to y. So basically what that's telling you is, like, if you just leave this y part off, like just the log to the base a of x part, that's saying like what that number is, it's what you would have to raise a to. So it's the power that you would raise a to in order to get x. So that would mean that this down here would have to be true, that if you raised a to the power of the log base a of x, you have to get x. So here you can see that they're inverses of each other, right? Because then you have two functions here, like really this is a composition, right? The inner function is taking the logarithm and the outer function is raising a to that power. So those two functions are going to be inverses of each other. Okay, fine. That's what the definition is, but what does this actually look like with some numbers? Well, the first few are just kind of rewriting things in terms of logs. So here we have an exponential statement, right? Because the 2 is being raised to an exponent of 5. If you rewrite this with logs, then you would write it like this, where it's the log the base 2 of 32 equals 5. So that's saying, what power do you have to raise 2 to in order to get 32? Well, it's 5. So that's what that log ends up being. Or with this one, if you raise 4 to the power of 1/2, you get 2. So then if you phrase it with logs, it would be log to the base 4 of 2 would be 1/2, right? Because this expression here, log to the base 4 of 2, is saying, well, what do you have to raise 4 to in order to get a 2 out? And you raise 4 to the 1/2 power. So when you do the conversion from exponential notation to log notation, the one thing that stays the same is the base. Because notice here, you get the base of 2, right? That's being raised to the 5th power. But when you rewrite it with the log, that's the base that you use for the log. Same thing here. We got 4 being raised to the 1/2, so 4 is the base. Then when you write this as a log, 4 is the base for the log. So that part stays the same. So if there's one piece that stays consistent, that's what it is. And there's one more of these, which is kind of a wild one here because you get a negative. But 1/4 raised to the power of -3 is going to be 64, because what you would end up with is 1/4 to the -3. And so then if you rewrite that with a positive exponent, it's 4 to the 3rd, which is 64. But then if you were going to rewrite that with logs, so notice same base, right? The base up here is a 1/4, base down here is a 1/4. So log to the base of 1/4 of 64 is going to give you -3, right? Because if you raise 1/4 to the -3rd power, you get the 64. Then you can also go the other way, and that's what these examples down here are. So what if you start off with log notation and you want to rewrite an exponential notation? So remember, again, even though we're going the other way, the base, the number that's the base in one format is also going to be the base in the other format. So here we've got base 7 log. So you say, okay, well then 7 squared must be 49, right? So the 7 is still going to be the base. And then you raise 7 to the 2nd power. Sure, you get 49 back out, right? Number 5, log base 2 of 1/8 is -3. So then same base, where I use the 2 as the base down here. So we're saying then 2 to the -3, I'll give you the 1/8, the 0.125. Down here, you can have a base that's irrational. You don't see it that often, but you could. And this is a case where it happens, because if you raise radical 5 to the power of 4, you'll get 25, right? Since radical 5 to the 4th is the same thing as 5 squared. So yeah, that's 25. The next page is log equations, and there's more than one way to do this, but I think it's easier to understand these when they're phrased in exponential form. It's easier to see what's going on. So that's the maneuver that I followed, and that's what our book does too. it does tend to make things a little bit easier to see. So basically what I did in these examples is I took something that was in log format, basically, and I rewrote it. So instead of having a log equation, if I rewrite that in exponential form, then I have an exponential equation. And for me, that's a lot simpler. So like here where it's log the base 3 of 81 equals x, first thing I did was rewrite that with an exponential function, or an exponential expression right here, the 3 to the x. So if this is true, it must be the case that if you raise 3 to the x power, you get 81, right? And that's this right here. But then to go back to earlier in this chapter, if you could somehow rewrite your equation so that the same base is on both sides, then you can set the exponents equal to each other. So I said, well, wait, 81 is 3 to the 4th. But then if 3 to the x is equal to 3 to the 4th, then x has got to be 4, right? Because if we've got the same base on both sides here, then you can set the exponents equal to each other. And at that point, at least for this problem, you don't have anything else to do. Here, I use the same move. X to the 6th is going to be 5 squared. And if you're thinking, why am I leaving that as a 5 squared and not changing it to 25? It's because of this next step, where I don't want x to the 6th. I want that solved for x. So we're going to have to take the 6th root of both sides, or raise both sides to the 1/6 power, however you want to view that. So then here, if I've got this written as a 5 squared, then I have an exponential expression raised to another exponent. So then I can just multiply the exponents together. That's why I didn't rewrite it as a 25. So then this ends up being 5 raised to the power of 2/6, which you can rewrite as 1/3. And then you just got x on the other side. All right, to keep this common thread going, where we start off with the log equation and rewrite it as an exponential equation. So from here, 4 raised to the power of negative 1/3 must be equal to x. So we've already got this solved for x. Now we just have to simplify the left side. So I rewrote it with a positive exponent. And then this last step, I don't know if you really need that. I mean, I think here the 1/4 to the 1/3 is good enough. But if you wanted to get it to where you had the smallest possible base, 4 is 2 squared, so you could rewrite 4 to the 1/3 as 2 squared to the 1/3, or 2 to the 2/3. Then going over to number 10, same move, 3 squared equals x minus 1, but 3 squared is 9. Then to get the x by itself, you just add 1 to both sides, and there you go. The two bases that show up the most frequently for logs, because you can have all sorts of bases, right? We saw a whole bunch of different ones, and you can have radicals, and you can have all different numbers and things, but the most common ones are base 10 and base e. And even though the base 10 is called the common logarithm, I would argue that the base e is actually one that you see more frequently because it shows up in like continuously compounded interest, exponential growth and decay, and like the way that bacteria grows, stuff like that. But in any event, these are the ones that have keys on the calculator. So the common log, the base 10, when that's written, usually the base is left out. So like here it's written in where you got the base 10 right there, but if it just says log x and there's no base written in, then it's understood to be 10. So if it's something else, then you have to be told, right? Like if it's base 2, you got to be told that it's base 2. But if it's base 10, it's just, if it says log x, you can just assume that it's base 10. And then when you have base e, you never see it written like this. It's always written like this, where the ln stands for natural log. Even though those letters are in the opposite order, that is what that stands for. So ln, whenever you see that, it's like, oh, that's a base e. And these do have calculator keys. So the calculator key that just says log, that's base 10. The one that says ln, that's the natural log, so that's base e. And then these examples have the base 10 and then the base e. So with the base 10, so to evaluate each of those expressions, I just turned it into an equation that then became a thing that was solvable. So log of 10 to the 4.3 power, I just said, all right, well, if I set that equal to x, then this is base 10, so 10 raised to the power of x equals 10 raised to the power of 4.3, which means x has got to be 4.3, right? And it's kind of the same move here, where then you say, well, it's base 10, so 10 raised to the power of x is going to be 10 raised to the power of radical 11, so x is radical 11. And then here, I guess this one is kind of similar. So this is base e, so e raised to the power of x is e to the 3/4, so x is equal to 3/4. This one's slightly different, where here if I set it equal to x, then I guess I also have to get the log expression by itself. So I divided both sides by radical 2, so that's what's going on here, because then we can say, well, then if this is base e, so e raised to this power on the right side would have to be equal to e to the radical 2. So x over radical 2 equals radical 2, and then if you multiply both sides by radical 2, you get that x equals 2. And actually, number 14, I wouldn't naturally do it the way that I have it written out there. I would actually use this, because that one had something out front, you can put it back up into the power. But these log properties, so with any base, the log of 1 is 0. That's because for any base that you want to pick, if you raise it to the 0 power, you'd have to get 1, right? 10 to the 0 is 1, e to the 0 is 1, 2 to the 0 is 1, right? That always happens. So no matter what the base is, the log of 1 is always 0. Then this generally would have to be true just by the definition of how logs work, that the log, the base a of a to the k would just be k, because it's, well, what would you have to raise a to get a to the k? You'd raise it to k. This third one is just showing that the exponential expression and the log expression are inverses of each other. So number 3 isn't anything new, but 4, 5, and 6 are interesting. In effect, they're shortcuts, but they're very, very valuable ones. So if you have the log of a product, then you can break that up into the sum of individual logs, or vice versa. Like if you have like some big long expression and you want to shrink it down, then I guess you would be going right to left instead of left to right. And then same thing with number 5. What if you have a quotient? If you have a log of a quotient, you can write that as the difference of two logs. That also ends up being helpful in both directions, sometimes going left to right, sometimes going right to left. And the last one, this helps too. If you have the log with a different base than you have here, right? So like a and x are supposed to be different numbers, at least in theory. Then you can bring the power out front. So that's the one that really, like, if you've never seen it before, that looks crazy. Right? Like, when do you ever get to do things like that? Right? That's not a thing anywhere else, but it is here. And that helps too. Like, it helps to be able to combine like terms and things and, you know, get a nice, like, efficiently written answer. But yeah, you can do that. If you have the log of some exponential expression, you can just pull the power out front like it is right there. And we're going to see some of that in these examples. So this first one, where it's log the base 4 of 6/7. So first you look at this, you go, oh, it's a quotient. It's number 5. Yep. So first step is you can write that as the log, or the difference of two logs. That's what I was trying to say. So log of the base 4 of 6 minus log of the base 4 of 7. But you could actually break this one up. Can't do anything here because 7's a prime number, right? I mean, you're going to write that as the log of 1 plus the log of 7. Doesn't change anything, right? Log of 1 is 0. So this one you can, though, because 6 factors, right? You can say, well, that's not prime. And you can write it as 2 times 3. But now we have the log of a product. So now this is like number 4 up above. And you can say, oh, well, that's the log of 2 plus the log of 3. Right? So now this one is stretched out into the smallest individual possible logs that you can have. Then number 16, kind of a similar idea here. First you look at this and you go, oh, it's a quotient. Yep. So we can write that as the difference of two logs. But then this part right here, 4p, that's a product. So then you can write that as a sum of logs. And that's what I did right here, where I've got the log of 4 plus the log of p. But 4 is not prime. It's 2 squared. And then you can bring the power out front, which is what's going on down here. I took that 2 from the exponent and brought it out front. And that's as far as that one would be able to get simplified down. The 2 underneath, number 17, I guess at first you look at that and go, it's a quotient. So that's what I did here. So log of the numerator minus log of the denominator. Also notice this is a base 10 log since the base isn't written in. But then x to the 5th y cubed, that's a product. So you can rewrite that as the sum of two logs. But then notice exponent, exponent, And I rewrote 9 as 3 squared because I was going to have to do it anyway, so I did it in this step. Also has an exponent. So we're going to bring those exponents out front, right? That 5 ends up out front, so does that 3, so does that 2. And so now that one is simplified as far as it can go. 18 is kind of an epic. So we got the log of this square root with a bunch of stuff going on under the radical. All right, well, first of all, I'm going to rewrite the square root as the log of all the stuff underneath, raised to the power of 1/2, because then I can use that exponent rule and I can bring that 1/2 out front. And that's where it stays for a while, and I'm going to simplify the rest of it. So the 1/2 for the time being is out of the way. Worry about what's going on inside the brackets here. It's a quotient, so we can write that as the difference of two logs. But then the thing that's in the numerator up here, so that's in this first log, that's an exponential expression. So you can bring that 5 out front, right? Bring that power out front. There's that. Also, 10 is not prime, so I rewrote 10 as 2 times 5. So this first part's done. There's nothing else you can do to this, right? X plus 1 is broken down as far as it gets. But then I guess here, you would rewrite this log as the sum of two logs, but because you're subtracting it, subtract there and subtract there. I guess be careful that this one's also got to be a minus, right? Because you'd be subtracting the entire sum and then I guess distributing the minus. So you end up here, and then I ran the 1/2 through it finally, just to get rid of those brackets, and you end up there. The next thing is going backwards. So what if you have a bunch of little logs and you want to combine everything together into a single log? Well, use the same steps, you just go in the other order. So here we've got a plus and a minus. And if you think of those rules, they're number 4 and number 5 on the last page. Plus should turn to a product, minus should turn to a quotient. So I'm just going to go piece by piece here. I'm going to deal with the plus first. And I said, okay, if you have the sum of two logs, you could combine that together into the log of the product of K and M, which is what that is. So that's number 4 just reversed, right? Just going right to left instead of left to right. But then we've got that minus, and we say, oh, well, if we have one log minus another log, we can write that as the log of a quotient. And that's what I did there, right? Km divided by A. That tail on that A is a little long. That was throwing me off for a second, but that is supposed to be an A. All right, getting over to this one. So this one's got a minus. So you think, all right, well, that's got to be a quotient. Eventually. You can only do that move if you have coefficients of 1 with the logs. So that 4 and that 3, we got to deal with them first. But that's that last rule. That's rule number 6, where now if we're going right to left, we say, well, we could bring the 4 up into that exponent. And we can bring that 3 up into that exponent. So that's what I did first. And I said, well, that's got to be equal to the log of a to the 4th minus the log of b cubed. And now, since the coefficients are 1 for both of these logs, then you can rewrite that as just a single log where it's the log of a quotient. And so then that's where you end up. Next, for ones that are a little bit longer, number 21. So this one's ready to go as far as using that minus to get back to just having the log of a quotient, but this one's not. We got to deal with that 1/2. Put that up in the power first. So that's what I did here, right? This first part doesn't stay the same at all. But this second part, I took the 1/2, I put it up there, and then we're good to go. Like now we're in business, right? Coefficient of 1, coefficient of 1. So then you can rewrite this as the log of a quotient. And I don't even know if you need this line here. I just rewrote the raising to the 1/2 power as a radical. So I guess that's just for aesthetic purposes. Number 22, this is about as intense as this can possibly get, I think. So, yeah, there's a minus. We're eventually going to have to use the quotient rule for logs, just the other way around, right? Just going from right to left. But we've got some coefficients we got to deal with. So here we got to bring that negative 3/4 up there, and here, I guess, a 2/3. So when you bring the negative 3/4 up, it's this whole thing that you're taking the log of raised to the negative 3/4. That's why I've got the parentheses here. It's not just going to be the p to the 4th. It's the whole thing. It's the 16p to the 4th. And same thing here. When you bring the 2/3 up, it's this whole thing that you're taking the log of now raised to the 2/3. So the 8p cubed, not just the p cubed. And then what I did was I distributed the exponents. So like here, I said, well, it's got to be 16 to the negative 3/4 times p to the 4th to the negative 3/4. And then I just rewrote the 16 as 2 to the 4th, because then the rule that you have to use about multiplying exponents looks a little more straightforward in the next step. That was the only reason I rewrote that 16 here. But then over here I rewrote the 8, since 8 is 2 cubed. And then again, that rule about multiplying exponents looks a little bit more straightforward or more streamlined. And then we have p cubed raised to the 2/3 power. So when you multiply the exponents together, I guess in all 4 spots, you end up here. And then this was the point where I said, okay, I guess I'll combine this together into the log of a quotient, which realistically you could do it back here if you wanted. But I kind of wanted to get some stuff simplified first. But once you get here, the 2 to the negative 3 and then the 2 squared in the bottom, these have the same base, so you could subtract exponents and say, well, then that's 2 to the negative 5th. And then the same thing here, the p to the negative 3 and the p to the negative 2, right? There's the p to the negative 5th. And then I just brought those down, so they're rewritten with positive exponents, so brought them down to the denominator. And then I just said, well, 2 to the 5th is 32, so I guess I could simplify that a little bit, but that's about as far as it could go. So that one's pretty intense. That's the mountaintop as far as these go. Like, that's as tough as they get, I think. I can't imagine there would be anything that had more steps than that one. But that's why I put that in there. So I could say that if you can follow along with this one, I think you're going to be okay with this. Using the calculator ought to be pretty straightforward, because presumably your calculator's got a log key and an ln key. Most do. The entry may be different. There are some Texas Instruments calculators where the model number starts with a 3, where the input to me feels backwards. Because like if I was going to do this, I would just hit the log key, then 147, and then enter. There are some calculators where you do 147, then log key, then enter. So I guess you'd have to kind of be aware of that, potentially. But that's pretty easy to catch from trial and error, right? Just try this, see if you get the right thing. And if you think about it, what you get here should be a little bit bigger than 2, just because here the base is 10, right? Since it's not written in. 10 squared would give you 100, right? So the log of 100 is 2. And then the log of 1,000 is 3, right? By the same kind of logic. So between 100 and 1,000, you go, well, this is a whole lot closer to the 100, so this ought to be pretty close to 2, the power that you have to raise 10 to get the 147. Yeah, it's pretty close to 2. And then down here, natural log of 0.014, that ends up being negative. If you take any log, so like base 10 log, natural log, whatever, of a number that's less than 1, you're going to get a negative. Just because in order to raise, I guess, well, unless your base itself is less than 1, then that's a different ballgame. But even if you had like a base of 2, in order to raise 2 to some power and end up with a number that's less than 1, you got to raise it to a negative power, right? 2 raised to the power of negative 1 is a half. 2 raised to the power of negative 2 is a fourth. Negative 3 is an eighth, right? So that's how you get values less than 1. It's with a negative power. So if you look at this and go, oh, that's weird. How do you get a negative? That's how. It's if you take the log of anything less than 1, assuming that your base itself is larger than 1, then it'll work out like that. But these are usually the only 2 bases that you're going to have in your calculator, right? Base 10, base E. So like the log, like just regular old common log, and then natural log. But then what if you want to use your calculator to evaluate a log where the base is not 10 and it's not E? What do? Well, use this change of base rule, where if you have your base A and it's not E and it's not 10, then you can write this you can rewrite it as a quotient of logs, and you can use whatever base you want. So now it's the log base B of X over log base B of A. And when you pick the other base, just pick one that your calculator can do. So either base 10 or base E. And I always use base E just because that seems to show up more often. But you can use base 10, you end up in the same place. So right here, I've got the log base 9 of 12. Calculator's not doing that, like not directly. So you've got to rewrite it first. So I said, well, then that's the natural log of 12 over the natural log of 9, and you get 1.131. You could use the base 10 logs if you want to. You end up in the same place. So base 10 log of 12 over base 10 log of 9, same answer, right? So either way should work. Number 26 is the exact same concept, right? Your calculator is not going to have a log key with a base of 1/2, right? So we're going to have to adjust here. If you use natural logs, it would just be the natural log of 3 over the natural log of 0.5, which ends up being negative 1.585. Or with base 10 logs, right? Same idea. You end up in the exact same place. If you want to get really fancy, you could rewrite the denominator like how here arrived the natural log of 0.5. You could rewrite that as the negation of the natural log of 2. That's correct, but if you're going to shove it into the calculator anyway, you might as well just do that without making any other adjustments.